In July of 1958, the New York Times told its readers about a machine the U.S. Navy had just unveiled. It was, they reported, the embryo of a computer that would one day walk, talk, see, write, reproduce itself, and be conscious of its existence. What it could actually do was tell a card marked on the left from a card marked on the right. That was the whole repertoire. 11 years later, a book by a man who went to the same high school as its inventor proved mathematically what it could never do. The funding vanished. The field froze for 17 years. Welcome back, and I want you to feel the ground change today because it genuinely does. 4 or 5 lectures we walked the web, Frontend, Backend, data, deployment, security. Every stretch of it shared one trait you probably didn't notice. A human wrote the rules. By hand. As code. Press this button. Change that screen. Today we leave that country for a continent where nobody writes the rules because the machine finds them itself. 2 questions. Why did rule writing stop working? And what does a machine actually do when it learns? Let's be fair to the old country first because people are rude about it and they're wrong. A rule-based system runs an input through rules a human wrote. Balance bigger than the amount. Send the money. Tax bracket, multiply, add, done. On that terrain, it's flawless, and anyone can see exactly why a result came out. A maze with a signpost nailed at every fork. Then somebody says, here's a photo. Is that a cat? Pointed ears means cat. Except the Scottish Fold's ears fold flat, so you're wrong on day 1. Patch it, pointed or folded. Now here's one shot in the dark, one in profile, and a cat in a box with nothing showing but 2 eyes. And your folded ears patch just flagged a floppy-eared dog. That's combinatorial explosion. The second wall is worse because it fights back. Picture an early 1990s spam filter. Rule. If the body contains the word free, it's spam. Worked great for about a week. Then the spammers wrote F, space, R space, E space, E. Add a rule. So they added an exclamation mark. Add a rule. All caps. Add a rule. This is whack-a-mole, except the mole has a business model. And here's the insight under both walls. A human cannot sit down and predict every exception in the world in advance and write it out, listing every possible look of a cat, every mutation of spam, by hand. That was impossible from the first line. So you flip the whole thing over, and the fix is one arrow pointing the other way. Traditional programming goes, data plus rules gives results. Machine learning swaps the ends of that sentence. Data plus answers gives rules. Show it the data and a pile of correct answers, and it finds the rule connecting the 2 by itself. That answer key is called a label. Finding the rules is called training. The lump of found rules you hold at the end is the model. Here's the analogy. Rule-based is writing down a recipe in words. Machine learning is making somebody taste 50,000 finished dishes until they simply know what delicious means. Nobody handed them the recipe. They just ate a lot. Back to spam. You write 0 rules. You hurl in tens of thousands of spam messages and tens of thousands of normal ones, and the only thing you attach is the answer. The model draws the boundary itself. Teaching by attaching answers is supervised learning. A teacher beside you with a grading sheet going right, wrong, right. The other fork attaches nothing. Dump the data in and say, group the similar ones yourself. That's unsupervised learning. And notice what comes out the far end. A model doesn't declare this is spam. It says 93% chance of spam. The world isn't sliced clean by a knife, so the answers aren't either. This idea is much older than you think. In 1952, an IBM engineer named Arthur Samuel loaded a checkers program onto an early IBM computer, and by 1955 it learned on its own. It played itself, endlessly, piling up which moves were good and which were disastrous. His 1959 paper on it is what lodged the phrase machine learning permanently into the language. 2 things about Samuel I can't get past. After retiring from IBM, he joined Donald Knuth's typesetting project Tex and wrote the early manuals, and he did not stop programming until he was 88. And that famous definition everyone quotes as his, about computers learning without being explicitly programmed, that sentence appears nowhere in his paper. A quote so clean nobody ever checked it. Now, one thing almost everybody gets wrong. People assume you dump the data in whole, and the model handles it. Before deep learning, absolutely not. A model doesn't swallow an email as a clump of letters. It receives only the signals pulled out from inside that are useful for judgment. Each one is called a feature, how often a certain word appeared, what the sender's domain is, how many links are buried in the body. The analogy is a resume. When someone sizes you up, you can't shove your entire life at them. The childhood, the bad haircut, the 3 years you'd rather not discuss. You trim it to 1 page. The model judges from that page, which raises the decisive question: who decides what goes on the page? In the machine learning era, the answer was still a human. What counts as a feature, how to process it, a person sat there and racked their brain. The work has a name: feature engineering. And it wasn't a chore at the edges. Same data, same algorithm, and performance swung wildly depending on which features you pulled. Practitioners passed it around as settled wisdom, tuning the features beats, swapping the model. But look at the limit hiding in there. Pulling good features is the handiwork of an expert who knows the field deeply, and that know-how is worthless the moment the field changes. Features that work on cat photos do nothing on X-rays. Rules had left the human's hands. Features hadn't. So, could we hand off that last bit of handiwork too? The thing that answered exactly that question is deep learning. And let's kill a piece of vocabulary confusion first, because the press mangles it constantly. Deep learning is not a separate new continent. It's a branch of machine learning, which is itself a branch of artificial intelligence. 3 circles nested. What makes it decisively different is one thing: a human doesn't need to define the features. Throw the data in nearly raw, and the model learns the whole chain in one bundle. That bottleneck that snagged human experts for decades didn't get solved. It got swallowed. To see how, look at the underlying structure, the artificial neural network. Grand name, embarrassingly simple part. The part is a neuron. It takes several inputs, multiplies each by a weight, adds them up, lays one baseline number on top called the bias, and passes the total through a gatekeeper called the activation function. Strong enough, it passes. Weak, it gets pressed flat. One neuron is nothing. Line several up, and you have a layer. Stack layers, and each crossing shapes the data into something more abstract. Lines and dots, then curves and corners, then eyes and ears. And that's what deep learning's deep means. Not profound, not wise. Nobody's neural network is contemplating anything. It means the layers are physically stacked deep. One specialist structure deserves its name spoken because it's what made images work, the CNN, the convolutional neural network. Its core is a small matrix called a filter. Picture a single small magnifying glass. You slide it across the image, and instead of taking in the whole picture, it peers at small patches. Is there an edge here? Is there a curve? And here's the kicker. What that magnifying glass looks for is not set by a human hand. During training, the model works out for itself that a filter catching this pattern is useful for recognizing cats, and adjusts the filter's own values. Rules left the human's hands. Now features have 2. Put the 3 eras side by side, and the storyline of this entire region shows up in one look. Rule-based. The input is data plus human-written rules. A human writes the rules. Features, not applicable. The answer is a clean-cut deterministic value. Machine learning. The input is data plus answers. The model writes the rules. A human still engineers the features. The answer is a probability. Deep learning. The input is data, nearly raw. The model writes the rules and extracts the features too. Read down those columns. The column a human touches empties out, one cell at a time. That march of empty cells is the plot. Which takes us back to 1958 and the machine from the top of this lecture. Frank Rosenblatt was a psychologist and an engineer, and he built the prototype of everything we just described, the perceptron. Inputs times weights, summed, fires when it clears a threshold. That's the neuron from 2 minutes ago, drawn in 1957, and he built it in physical hardware with Navy money. Then he talked it up at a Navy press conference. The Times picked it up, and a machine that could tell a left-marked card from a right-marked one was announced to the world as the embryo of something that would walk, talk, see, write, reproduce itself, and be conscious of its existence. Reproduce itself. 1958. That's the historical prototype of the AI hype cycle. Enter Marvin Minsky, co-founder of the MIT Artificial Intelligence Laboratory, absolute titan of the field, and also the man who most effectively hobbled neural networks for a generation. Here's the twist. In 1951, Minsky built a machine called SNARK, 40 vacuum tubes imitating 40 artificial neurons, training a virtual rat to run a maze. One of the first neural network learning machines ever built. And then in 1969, he published a book called Perceptrons, proving mathematically that a single-layer perceptron can't even learn XOR, a problem simple enough to draw on a napkin. The man who first built neural networks buried them most effectively. And one more thing. Rosenblatt and Minsky went to the same high school. The evangelist and the executioner, same hallway. Funding agencies read that book as proof that neural networks were a dead end, and the money drained off toward symbolic AI. That's the first AI winter. 17 years. And here's the detail that should genuinely annoy you. Minsky already knew that stacking layers would represent XOR just fine. He said so in the book itself. The problem was never that multi-layer networks couldn't work. The problem was that nobody knew how to train one. There was no method for fixing the weights buried deep inside the stack. A field sat frozen for 17 years because one procedure was missing. Rosenblatt never saw it filled in. On his 43rd birthday, in 1971, he drowned in a boating accident. So let's go get that missing piece, which means finally answering the question we've been dodging. What does the model finds it by itself actually mean mechanically? A freshly built neural network is not a blank slate. It's a nonsense slate. Every weight in it is a random number, so you show it a photo of a cat and it answers, with total confidence, 72% chance that's a car. Training is whittling that nonsense down. And to whittle it down, you first have to measure it, one single number for how wrong was that. The ruler that produces it is the loss function. And now training has exactly one goal. Make that number smaller. Fine. Which weight do you nudge and which way? A network holds millions of them, so you need to know how much each one is to blame for the final error. Calculating that blame in reverse, starting at the output, tracing backward toward the input, is backpropagation. Picture a company whose quarterly numbers just cratered. You work backward. This much is on the division, this much on the team, this much on you personally. And that is the piece that was missing for 17 years. In 1986, David Rumelhart, Jeffrey Hinton, and Ronald Williams published a paper in Nature that was barely 4 pages long, laying out how to flow the error backward and correct even the innermost weights. A 17-year bolt slid back by 4 pages. Now, you know which way is downhill. Imagine you've been dropped on a mountain in heavy fog. You want the valley floor, the lowest loss, but you can't see the terrain. All you can do is feel the slope under your boots and take one step, then another. That's gradient descent. Backpropagation is the compass. Gradient descent is lifting your foot. And one setting here is brutal. How big is one step? That's the learning rate. Step too big, and you'll bound clean across the valley floor and up the opposite slope, then back again forever, an extremely enthusiastic hiker who never arrives anywhere. Step too small, and you're taking baby steps into the next century. Also, the fog is real. You stop in whatever valley you fell into, and nobody promised it was the lowest one. So more training is always better, right? There's a trap. Picture a student who, the night before the exam, memorized nothing but a leaked answer key. On last year's paper, they nail every comma. Then the real exam hands them last year's question with one small twist, and they collapse because they never learned the principle. They learned the answers. That's overfitting. Accuracy on the training data goes near perfect, while accuracy on data the model has never seen falls off a cliff. It memorized the noise that happened to live in that one pile of photos. Which is why 99% accuracy on training data is not a brag. It's an alarm. When the gap between the two scores is wide, you have a memorizer, not a model. 3 weapons against it, all the same idea in different hats. Don't let it lean too hard on any one thing. Dropout randomly switches off a portion of the neurons for a moment, over and over, throughout training. Why does that help? It stops the network leaning on a few star neurons. It's a group project where the professor randomly benches a few members every round, so you can never end up with one ace plus 4 people coasting. Regularization slips a penalty into the loss function. Let a weight grow abnormally large, and I dock you points. And early stopping means putting the pen down before the validation score starts getting worse. Training isn't as long as possible. It's also knowing when to stop. So the idea has been complete since 1986. Why does nothing happen for another 26 years? Because the idea was there, and the fuel, the engine, and the tools were not. Around 2012, all 3 ripened at once. Fuel, data. A neural network is hungry, millions of examples just to get halfway smart, and specifically labeled data. The internet and a camera in every pocket finally made that possible. Engine, GPUs. Training is mostly multiplying and adding giant grids of numbers, absurdly many times. A CPU is a handful of very smart office workers. A GPU is thousands of laborers crammed in one room who can each only do simple arithmetic. It was built to color game pixels, and it happened to fit this perfectly. Tools, cloud, and open source. The starting gun went off in 2012. A deep learning model called AlexNet entered the big ImageNet recognition contest and posted an error rate of 15.3%. Second place was 26.2%. In that contest, victory normally comes down to 1 or 2 percentage points. AlexNet won by more than 10. That's not a better score, that's a different sport. And my favorite part is where it ran. Not a national lab. AlexNet was trained on 2 consumer gaming graphics cards in a graduate student's bedroom at his parents' house. The model that opened the modern AI era was rendered next to somebody's laundry. But that fuel didn't appear by accident. Somebody built it on purpose. In 2006, when nearly all AI research was obsessed with models and algorithms, Fei-Fei Li bet the other way. The bottleneck is the data. She solved the impossible labeling problem with crowdsourcing 49,000 workers across 167 countries. Her backstory is not a normal professor backstory. She emigrated to the United States at 15 with almost no English and almost no money. Her family opened a dry cleaning shop, and because she was the only one who spoke English, she ran it remotely from campus while doing a PhD at Caltech. She was answering the dry cleaner's line in the middle of physics problems. And when she unveiled the largest labeled image set in the world, the response was a polite shrug. Meanwhile, deep learning's first real-world win had already happened in 1989. Yann LeCun's team at Bell Labs pointed backpropagation at an actual job, reading handwritten postal codes for the U.S. Postal Service. About 95% accuracy. The first neural network to read human handwriting. By 1998, his team had a system reading millions of bank checks a day. And then it got shelved. Through the 90s, statistical methods took over and convolution was pushed to the fringe for 20 years. A correct idea born in the wrong decade. Waiting. It wasn't rehabilitated until AlexNet detonated, and the person who stood up and publicly called AlexNet a clear turning point in the history of computer vision was LeCun himself. Which leaves Geoffrey Hinton, who outlasted both winters. When believing in neural networks was close to professional suicide, he held one conviction: the key to intelligence is the brain's enormous parallelism. That bet cost him decades of being publicly wrong. He co-wrote the 1986 backpropagation paper, and in 2024, as a man who is not a physicist, received the Nobel Prize in Physics. And here's the scene I refuse to leave out. In December 2012, he and two students formed a company with no product whatsoever, and a secret auction broke out at a conference hotel, bidders raising by $1 million an hour. Hinton has a back injury that makes sitting agony, so he ran it standing up, laptop balanced on an upside-down trash can he'd flipped onto the hotel desk. Around midnight, the bid hit $44 million, and he went to bed. After that, deep learning ran the table. Speech recognition is why your phone started transcribing you on the spot. Translation took a real turn. Machine translation used to chop sentences into pieces and stitch them back together statistically, which is exactly as clunky as it sounds. In 2016, Google tore that out and installed an encoder and a decoder. The encoder reads the whole source sentence and compresses its meaning into one bundle of numbers, and the decoder unspools it into the target language. And that same year, AlphaGo beat Lee Sedol 4 games to 1 at a game machines were supposed to be decades away from. It trained by studying human games, and then by playing itself, endlessly. Which, if you're paying attention, is exactly what Arthur Samuel's checkers program was doing in 1955. But by around 2018, two walls were showing, and both are about language. Here's why language is hard. Starting from the first inch, a computer handles only numbers and apple, affection, and ladder are letters. In 2013, Google's word 2vec gave an elegant answer. Words that show up in similar contexts have similar meanings. King and queen appear in the same kinds of sentences constantly. King and banana, essentially never. So you train on an enormous pile of text and place every word as a point in a high-dimensional space. Then the uncanny part, arithmetic, works. Take king, subtract man, add woman, and you land right next to queen. Turning a word into a fixed-size vector like that is called embedding, and get your eye used to that word because the next region is built on it. Word 2vec had one fatal gap. One word, one vector, fixed forever. Take the word bank. A riverbank, or the place holding your money, same vector every time. It pinned the word as a point, but never saw where in the sentence it was sitting. So models that handle order arrived. The RNN and its cousin the LSTM, which read the way a person does, front to back, one word at a time, carrying a summary on a fixed-size notepad. And then they hit their own two walls. First, over a long passage, information from the front fades on the way to the back. It's the game of telephone, where what you whispered at the start comes out the other end as something about a horse. Second, an RNN is sequential by construction. You must finish the previous word before starting the next, so it cannot use the one thing that made deep learning explode. Now, the practical half, how you put this into an AI instruction. It's the compass for deciding, should this be written as rules or trained? A bad instruction is write me code with if statements that judges whether an uploaded photo is inappropriate. That's ordering a combinatorial explosion. A good one names the terrain. This can't be written rule by rule. Call an already trained image classification model through an API. Second, never accept a training accuracy brag. Ask for the score on data the model hasn't seen, and if the gap is wide, say the word overfitting out loud. Third, when training goes badly, point at the knob. If the loss drops and then spikes, lower the learning rate. Let's tie it together. 2 ridges today. The first, we left the plains of determinism, where a human wrote every rule by hand, because those rules break the moment the world stops behaving. Combinatorial explosion on one side, maintenance hell on the other. So the arrow flipped. Instead of data plus rules giving results, it's data plus answers giving rules, and the output stopped being a verdict and became a probability. Then features. In the machine learning era, a human still had to sift the useful signals out by hand, and that expert handiwork was the real bottleneck. Deep learning didn't solve it. It swallowed it. The second ridge. What training actually is. Measure the wrongness with a loss function. Assign blame backward through the network with backpropagation. Take one step downhill with gradient descent and set the size of that step with the learning rate. Repeat a few million times and a pile of random numbers starts calling a cat. It isn't magic, it's stubborn repetition. And the one sentence to carry out of here. The idea was finished in 1986 and then sat there, useless, until data, GPUs, and open source ripened 26 years later. This technology was never held back by its ideas. It was held back by its fuel. Ideas that look dead are usually just early. Everything in this lecture comes from Region 5 of a book called the AI Development Atlas. It's built on one idea. In the age of AI, the person who commands the tool isn't the one who memorized the most syntax. It's the one who knows the terrain, who can look at the map and say, precisely, the problem is right here. 10 regions, from the front end all the way through AI transformation, each drawn as ground you can actually walk, with the people who first traced it. If this trail made sense to you, the full atlas is available right now, and the link is in the description below. Next time we walk straight into the two walls we just hit. Long context and parallel processing. The thing that smashed through both at once in a single paper is the reason you can talk to a machine at all today. Region 6, the transformer, attention, and the large language model. If this was useful, subscribe, and I'll see you on the next trail. DK Corporation know the terrain. Command the tools.